This series of lectures concerns another interesting application of integration to physics, in particular to statics, called the calculation of center of mass of a system. Eventually, a system will refer to a plate of uniform thickness and density. But to start off, the system that we'll discuss in the calculation of center of mass will be for a finite collection of masses. We'll start with just two of them to make things really simple. And so for this introduction, let us suppose that we have two masses of mass m1, and m2, which have been carefully positioned along, if you like, a seesaw or a horizontal surface. And here we have carefully oriented a coordinate system so that 0 appears right here. So let us suppose that mass m1 is at an x-coordinate of x1, and here x1 looks like it's probably a negative value since it's to the left of the origin. And we position m2 so that its x-coordinate is over here at x2, which looks like it should probably be a positive x value. Now, before we get around to the center of mass of this system, we'll define an important quantity going forward for each of these masses. Each of these masses, let's do it for m1 first, has what we call a moment about the origin. The moment of mass m1 is defined to be the mass times the position. And by position, I mean the x-coordinate with respect to the origin. So the mass here is m1, and the position is x1. So that's the moment of mass m1. And similarly, the moment of mass m2 is found in exactly the same way. You multiply the mass, of m2 times its position to get m2 x2. So our goal now is to find what we'll call the center of mass of this system. What we would like is, again, to think of this as a seesaw, which is positioned or balanced about the origin. If the masses m1 and m2 are not equal, and if these distances x1 and x2 are not equal, then we might expect in general the system to have a tendency to rotate either one way or the other. For example, if these distances x1 and x2 are the same or symmetric about the origin, and m2 is much heavier than m1, then the thing will rotate in this way, as we expect a seesaw to do. We would like to find that point along the x-axis, maybe here, or here, somewhere along the x-axis, about which the system will balance perfectly. We call that point the center of mass of the system. And in general, it is defined as follows. The center of mass is defined to be the sum of moments divided by the total mass of the system. In this case, we get, well, the sum of the moments. There are only two moments, so we have the first moment plus the second moment divided by the total mass, which is just the sum of the masses, m1 plus m2. So there we go, center of mass. Let's do a very quick example. For this example, let's suppose we have, again, two masses, one positioned at -2 meters, the other one at +3 meters. First mass, 5 kilograms. Second mass, considerably larger, 15 kilograms. The moment, or the moments of these components are as follows. The first mass has moment 5 times -2, or -10 kilogram meters. Those are units of moments. The second mass has moment 15 kilograms times 3 meters, or 15 kilograms per meter. And therefore we find the center of mass by summing these moments, -10 plus 15, and dividing by the combined total mass of the system, 15 plus 5, to obtain 5/20, or 1/4. And if you look carefully, all of these units are going to cancel out to leave you with nothing left over but meters. Center of mass is often denoted by x bar. X for x coordinate, going back and forth this direction. Bar is often denoted to suggest some kind of average, in this case an average of moments. So the interpretation of this, of course, is this. If you want to place a fulcrum point or a balance point at some place along this x-axis so that this system will balance perfectly, you'll do it at exactly 1/4 of a meter, right in here somewhere. That is the balance point or the center of mass of the system. Now you can see how this calculation would go if you had not 2 masses, but say 3 or 4 or 5 masses. You would just have contributions of more and more moments, and the total mass would be the sum of the masses of the components. I'd like to do another example now, this time not with 2 but with 3 masses. And the other significant difference with this example from the previous one is that now I'd like to calculate centers of mass both along the x direction here and also along the y direction here. So you can imagine that this system, if these masses are distributed and somehow positioned in space, that this whole system might have a tendency both to rotate around the x-axis and also have a tendency to rotate around the y-axis. And just the same, you might imagine that all of these masses are somehow suspended in a weightless medium or plate, and that what we're looking for is that one special position somewhere on this plate, maybe somewhere about right here, where we could balance the whole two-dimensional plate on the head of a pin so that it would rotate neither in the x nor the y direction. That special point, again, will be the center of mass of the system. The difference, however, is that that center of mass will have not just one but 2 numbers, an x and a y coordinate. So to find that center of mass, we need to go back to the notion of moments and redefine moments with respect to both the x and y coordinates. And we'll do that in just a moment. But to do so, let's add some numbers here. We need to keep careful track of the positions of these masses as we did before. Let's add some x and y coordinates. Let's say M1 has a mass of 3 kilograms and is located at x equals 4 and y equals 2. Let's say M2 has a mass of 7 kilograms and is located at x coordinate -5, y coordinate 3. And let's say M3 has a mass of 5 kilograms and is located at x coordinate 3, y coordinate -6. Those look like plausible coordinates, where these are positioned in their various quadrants. Now let's go back and let's consider M1. The moment of M1 about the y-axis measures the tendency of M1 to tilt or rotate the system if the y-axis is considered as a fulcrum. So this tendency of M1 to tilt the whole system around the y-axis is defined to be, well, the distance away from the y-axis times the mass. Now the distance away from the y-axis of M1 is precisely the x-coordinate of M1. So that's 4 meters times 3 kilograms, or 7 kilogram meters. And again, this is the tendency to rotate about the y-axis. Another word that might be helpful to understand is that this moment of M1 about the y-axis is the tendency of M1 to torque, I'm using that as a verb, to torque the whole system about the y-axis. Right? So we can similarly define the moments of all of the other masses about the y-axis. I'd like to find the total moment of the system about the y-axis. So I'm not going to do it right now, but you could similarly define the moment of both M2 and M3 about the y-axis, and it is an analogous computation. But I want the total moment about the y-axis. And that will be found just by summing the moments of each of the contributing masses about the y-axis. So for that we have -13, and again our units here for a moment are kilogram meters. And again, we can think of this number as a measure of the torque of the system about the y-axis. The fact that this number is negative means that this whole system will have a tendency to torque or rotate in this direction about the y-axis. Or that the center of mass, at least in the horizontal direction, is somewhere over here, because we're getting a negative number. Now we're going to calculate a similar number. Oh, and by the way, I should say, this total moment about the y-axis is often denoted capital M for moment sub y for y-axis. And again, it is the nature of these coordinates that to find the moment about the y-axis, you need the x-coordinates of those points. X-coordinate, x-coordinate, x-coordinate. In a completely analogous fashion, we can calculate what we'll call the moment about the x-axis. And that will be obtained by collecting all of the individual moments about the x-axis for the individual pieces. And this time we need not the y-coordinates, but the x-coordinates of these points. I'll fill these in, but they'll go in this box here, here, and here. What are those x-coordinates? For masses 1, 2, and 3, going back up to our figure, those x-coordinates are, the y-coordinates are 2, 3, and -6. So let me say it one more time. For the calculation of the x moment, we need the y-coordinates. For the calculation of the y moment, we need the x-coordinates. So here we have a total number, what is it? 6 plus 21 is 27, minus 30 is -3 kilogram meters. Now, we have moments about the x and y axes. The last step is to find the center of mass. And again, we'll do this one coordinate at a time. The center of mass along the x-axis is found, is denoted x bar, and that is found by taking the y moment and dividing by m, which is the total mass. And in an analogous fashion, the center of mass about the y-axis is found by taking the x moment and dividing that by the same total mass. The total mass for this particular system is, m equals, returning back up to the system, we have masses of 7, 3, and 5 kilograms. So total mass is 7 plus 3 plus 5, or 15 kilograms. And so we obtain for our x center of mass, x bar, the y moment, which is -13, divided by 15. And for the y center of mass, we need the x moment, which is -3, divided by 15. Or if you want to assemble those into one ordered pair, you just have -13/15 and -3/15. So this coordinate, this is just shy of -1. This is about 1/5, or -1/5, right? And so we go back up here, -1, maybe somewhere about here, -1/5. Our center of mass for this whole system is somewhere in the third quadrant. Yeah, does this make sense? Well, my drawing isn't perfect, but if it were, it would make pretty good sense, because if my drawing were really good, it would clearly show that this center of mass lies within this imaginary triangle which connects these three masses. So you have a lot more weight contributed by this mass and this mass. So the center of mass of this triangle, with masses all centered at the vertices, would be really close to this edge over here. And that's where you would balance the system.